All right, here we go with the first notes in Unit 2, which talks about the unit circle and graphing trig. But before we get into the unit circle and graphing trig, I just want to talk about the trigonometric ratios. So let's start with this warm up. Here I have triangle CAT with side lengths 3, 4, and 5. I want to find the cosine, sine, and tangent of angle T. So I'm looking at the bottom right of this triangle, angle T, and I have to find those trigonometric ratios. Now you may remember before the trick SOHCAHTOA. Now SOHCAHTOA is a nice little handy tool that we use to remember the trigonometric ratios, where sine is the ratio of the opposite and the hypotenuse, cosine is the ratio of the adjacent side and the hypotenuse, and the tangent is the ratio of the opposite side and the adjacent side. So finding the cosine of t, I'm looking at angle t. I know cosine is the adjacent over hypotenuse. So the adjacent side to t is 4, and the hypotenuse, always the largest side, and always across from the right angle. So we have 5. So adjacent over hypotenuse is 4 over 5. Sine of t, well, we know sine is the opposite over the hypotenuse. So opposite angle t is 3, and the hypotenuse, again, 5. So the ratio is 3/5. Likewise, tangent is the opposite over adjacent. So the opposite side, again, 3, and adjacent, 4. So the ratio, 3/4. Anytime we're finding these trigonometric ratios, I recommend writing out SOHCAHTOA, just as a reminder. Let's take a look at some special right triangles. So here I've got a 30-degree angle, a 90-degree angle. We know that the sum of the interior angles of a triangle is 180. Therefore, this last angle must be 60 degrees. So we've got a 30, 60, 90 triangle. Now, based on what we know about 30, 60, 90 triangles, we know that, let me go ahead and label this. We know that if the side across from 30 is x, well, then the side across from 60 is x root 3, and the hypotenuse is 2x, so double that side across from 30. So, using that, we know that the hypotenuse is double the side length across from 30. So if the hypotenuse is 4, well, that would be double 2, or half of 4, 2. So then the sine of 30 is, again, SOHCAHTOA, opposite over hypotenuse, 2 over 4, which reduces to 1/2. We know that across from the 60 is x root 3, or in this case, 2 root 3. So then the sine is opposite 60 over the hypotenuse, so 2 root 3 over 4. So we have 2 root 3 over 4, which reduces to just root 3 over 2. Go ahead and try number 2 on your own. You can pause the video and unpause once you got it to check your work. All right, go ahead and check your work. You may have noticed that the ratios of the side lengths is the same as before, 1/2 for the sine of 30 and root 3 over 2 for the sine of 60. Now, I want to try one more. Let's find the tangent of 30. So the tangent of 30 is opposite over adjacent, so that would be 5 over 5 root 3, opposite over adjacent. So then we need to rationalize the denominator. So we have 5 root 3 over 5 times 3, or 5 root 3 over 15, which reduces to root 3 over 3. So the tangent of 30 is root 3 over 3. Let's take a look at some 45, 45, 90 triangles. So down here for numbers 3 and 4, we've got a right triangle with one angle defined as 45. Well, again, the sum of the interior angles in a triangle is 180. So this remaining angle must be 45. So this is an isosceles right triangle. Okay. We know 45, 45, 90 triangles. If we say that the legs of the isosceles triangle are x, then the hypotenuse is x root 2. And that's for a 45, 45, 90 triangle. So using what we know, let's find the sine of 45. Well, we know the hypotenuse is x root 2, and we need the side lengths. So if the hypotenuse is 2, and we know that can be represented as x root 2, let's find our side length, x. So if we have this equation, 2 equals x root 2, then x must equal 2 over root 2, which, rationalizing the denominator, we have 2 root 2 over 2, or just simplifying, just root 2. So that must mean that our side lengths are the square root of 2. So we haven't found sine of 45 yet. Let's take that ratio. So opposite over hypotenuse, root 2 over 2. And that is the sine of 45. Go ahead and try number 4 on your own. Pause the video and check your work. All right, check your work. You may notice that the sine of 45 always is root 2 over 2. So that ratio stays the same no matter what the side lengths are. All right, let's try a few more. Go ahead and flip the page. So in summary, no matter what the size of the triangle, we'll always have these same ratios of the side lengths. So if we're looking at a 30, 60, 90 triangle, sine of 30 is always going to be 1/2. Sine of 60 is always going to be root 3 over 2. And then sine of 45 is always going to be root 2 over 2. Again, these ratios will always be consistent for all triangles, no matter what the size of the side lengths are. Okay. We can evaluate the sine, cosine, and tangent of any angle. That can be boiled down to a 30, 60, or 90, or 45, 45, 90 triangle. So what I mean by boiled down refers to what we're going to see later, reference angles. Okay. Before we talk about that, let's take a look at this here. Betty is a figure skater. While practicing, she does a turn that it measures 990 degrees. I want to know how many times does she turn around? Well, we know that one full revolution is 360 degrees. Therefore, 2 revolutions is 2 times 360, or 720 degrees. We have to rotate an additional 270 degrees to get to 990. So the total amount, she does 1 turn, she does 2 turns, so another 360, and then she does a 3/4 turn, or 270 degrees. So the sum here, 360, 360, and 270, that's our total, 990. Well, this is 1 full turn, 2 full turn, and then a 3/4 turn. So this implies that we have a 2.75 rotations around. So 2.75, or 2 3/4 times that she turns around. Okay? So assume she's facing the north of the ring. So if we were to assign direction, we're going to say that's north. She does 2 3/4 turns. So if she starts facing north, she goes around 1 revolution. She goes around a 2nd revolution. And then she goes around 3/4 of a revolution. Which way does she end up? Well, she ends up facing the east direction. Let's take a look at this angle below. This measures 60 degrees up from, we can call this the positive x-axis, if this is the coordinate plane. Then I want to find 3 other angles that measure the same place. We want it to land at this same place, this terminal ray to be the same place. Okay? So we know that just going up 60 degrees from the positive x-axis is that ray. But if we go, say, 60 degrees and then a full rotation around, so something like this, that would be 360 plus that 60 degrees. So we would have to go 420 degrees from the positive x-axis. We could go around another time. So let's continue on. Go around another full revolution. So adding another 360 degrees, that would be 780 degrees. And we could continue adding on 360 as many times as we want and find infinitely many angles that land at the same place. But instead of going counterclockwise, let's go clockwise. So how far would we have to go around clockwise to land at the same place? Well, it's less than one full revolution, particularly 60 degrees less than one full revolution. So we could say that it's 300 degrees the other direction. So to denote the other direction around, we want to say that it's negative. If counterclockwise is positive, clockwise is negative. These angles, including the 60 degrees, are all coterminal angles. Coterminal means that they end at the same place. They are coterminal. So the terminal ray lands on the same spot on the plane. So let's find the terminal, I'm going to say ray, so you can cross that off and write ray. Draw the terminal ray of an angle that measures 150 degrees on the axis below. So whenever we're drawing these angles, you can put a little note here. You want to start on the positive x-axis, just like we did before. Positive x-axis. Likewise, we measure our angles in the positive direction going counterclockwise. So counterclockwise means we are measuring our angles in the positive direction. Just like how we went in the clockwise direction, we got a negative angle. We can go in the counterclockwise direction and get a positive angle. So if we want positive 150, we're going to start on the x-axis. We're going to go around 150 degrees. So we know that if this is 0 degrees, then going straight up would be 90 degrees. All the way around, halfway around the circle is 180 degrees. 3/4 of the way around is 270 degrees. So 150 degrees from 0 is going to be past 90, all the way not quite to 180. So you can sketch that graph, that angle, that terminal ray, to measure right around here. That's 150 degrees. Let's go ahead and label that. Now, I want to know what's the measure of the acute angle formed by the ray we just drew and the x-axis. So the x-axis, the horizontal axis, I want that acute angle. So that smaller angle, less than 90, right here. That little angle here. Well, if this is 150, the x-axis is 180, that acute angle must be the difference, or 180 minus 150, which is 30 degrees. So that acute angle right there, that inside angle, is 30 degrees. That's what we call the reference angle. So to formally define it, we have the reference angle is defined as the positive acute angle formed by the terminal ray of an angle and the x-axis. All right, let's use the reference angle in a few examples. Go ahead and flip the page. So let's practice a few examples. Here I have 220 degrees. We're going to, again, start on the positive x-axis, and we're going to go counterclockwise, 220 degrees. So we're going to start, if we go up here, that's 90 degrees. Continue going around. A half rotation is 180 degrees. 220 degrees is just before 3/4 of the way around. So our ray, our terminal ray, is going to be in quadrant 3. Okay, so 220 degrees around is going to land in quadrant 3. So that's our terminal ray. Now, what is the reference angle? Again, it's the positive acute angle formed from the terminal ray and the x-axis. Well, I'm looking at the negative x-axis here. So that's 180. This is 220. And the difference, or that angle in between, is going to be 40. So that's our reference angle. Let's try another, 750. So this is greater than one rotation. So one rotation around would be 360 degrees. Another rotation around would be 720 degrees. And we got to go a little further, 750 degrees. So we're going to land in quadrant 1. That's our terminal ray. This is 750 degrees. And actually 2 rotations around, 0 rotations would be 0 degrees. 1 rotation around would be 360. 2 full rotations around would be 720. So the difference between our terminal ray and the x-axis, the positive x-axis, is our reference angle, 30 degrees. Let's try another. Here I have negative 110, so that tells me to go clockwise 110 degrees. So starting here, I'm going to go clockwise. It's past 90. Our terminal ray is going to be in quadrant 3. So this denotes negative 110 degrees. Now the reference angle is going to be the acute angle, positive acute angle made between the terminal ray and the x-axis. So if this is negative 180, then our reference angle is going to be the positive acute angle here. So that would be 70 degrees. All right, let's try a few more examples. Let's try negative 135. So we're going to go clockwise around. We're going to go 135 degrees. So down here is 90 degrees. Halfway in between 90 and 180 is 135. So our terminal ray is going to land in quadrant 3. Okay, this is negative 135. The reference angle, the positive acute angle made from the terminal ray and the x-axis, this little angle here, that is going to be 45. Let's take a look at what's going on here. Let's drop a perpendicular. We'll choose any point on the ray, and we'll drop a perpendicular to the x-axis. Always remember that it's to the x-axis. Okay, that's what defines a reference angle, is the angle made to the x-axis. So this reference angle is 45 degrees. We're going to drop a perpendicular and see what happens here. We've got a triangle, particularly a isosceles right triangle, a 45, 45, 90 triangle. So all of these special right triangle rules apply here. So to find the sine of negative 135, that is the same as finding the sine of a 45, 45, 90 triangle, the sine of 45. So we already know that ratio. That is root 2 over 2. But in this case, consider where the point lies on the plane. We're in quadrant 3. So this vertical distance is negative. Likewise, this horizontal distance is negative, and the hypotenuse of that triangle is always going to be positive. Okay? So the sine, opposite over hypotenuse, negative over positive, means we have negative root 2 over 2. Let's find the cosine of 135. Well, we already have our reference angle. We already have our triangle. So the cosine is adjacent over hypotenuse. We already know the ratio of the cosine of 45 is root 2 over 2. And again, adjacent over hypotenuse, negative over positive, tells us we have negative root 2 over 2. Let's try one more example. Here I have 390 degrees. So that's more than one rotation around the plane. So we have 360. An additional 30 degrees would take us to 390. So that would mean our terminal ray is in quadrant 1. The reference angle, I just said it, is 30 degrees. That's the acute angle made between the terminal ray and the x-axis. Let's drop a perpendicular and get that triangle. So notice what we have here. We've got a 30, 60, 90 triangle, a special right. Oh, here's our reference angle, 30 degrees. So the sine of 390 is the same as the sine of 30. So the sine of 30 we already know is 1/2. And then the tangent of 390 is the same as the tangent of 30, which we found on the first page. That is root 3 over 3. All right, I know there was a lot in this video, so go ahead and watch it through again if you feel like you'd benefit from that. But otherwise, we'll get a whole lot of practice on this, and we'll see you tomorrow in class. Have a great day, everyone.